Hello, Chem 152 students. We have concluded chemical kinetics. Now we're going to start something that's going to play a big role in the future of this course, which is chemical equilibria, where instead of looking at reactions that go from reactants to products in one direction, we're going to actually start looking at reactions that are reversible. They can go back and forth and eventually reach a point where the concentrations of reactions and reactants and products are no longer changing, even though there are still reactants becoming products, but at the same time that reactants are becoming products, products are becoming reactants, and so effectively the concentrations of each species does not change. So here's essentially what we're going to be looking at. We're going to be looking at the equilibrium constants, capital K, EQ, and effectively we're going to basically plug in concentrations of the products divided by the concentration of the reactants with a caveat. We will not take into account anything that is in the solid state, and we will not take into account water if it is in the liquid state. Therefore, we'll look at anything that's in a gas state, that's aqueous, that is liquid, as long as it's not liquid water. And yeah, basically, that's what we're going to do. So just an example of this generic chemical equation right above. We're going to basically just start solving for we're going to have essentially one giant fraction, where essentially we have the concentration of the products on top raised to exponents. And in this case, unlike with instantaneous reaction rates, the exponents for an equilibrium constant will actually be the stoichiometric coefficients. So for the concentration of reactant D, we will raise that to the value of lowercase d, and we will multiply that by the concentration of reactant A raised to its stoichiometric coefficient. And we will also take the concentration of reactant A in the denominator and raise it to its stoichiometric coefficient of lowercase a, the concentration of B raised to lowercase b, and the concentration of reactant C raised to lowercase c. And what I should add is that for the equilibrium constants, these are going to be the concentrations that are at equilibrium. These are not going to be concentrations at any other point. So as long as you are told that the concentrations you are looking at are at equilibrium, you can solve for that chemical equation's equilibrium constants. And one more thing I should note, the equilibrium constant is temperature dependent. What that basically means is the value that you get for the equilibrium constants, it can change, it can become different at different temperatures. But essentially, as long as you have these concentration values, that's all you need to worry about. KEQ will change with temperature, but also the concentrations that are needed to reach equilibrium will change as well. So just know that overall, this entire expression is only valid at unique temperatures. At one particular temperature, you need certain concentrations to achieve equilibrium. At a different temperature, you'll need different concentrations of products and reactants to once again get an equilibrium expression. And something to note is essentially the equilibrium constant is unitless. It does not have units. And the reason being is because essentially what we're doing in the brackets of each is we're not just taking the concentration. We're not just taking the concentration of, say, reactant D, which is in molars. But essentially what we're doing is we're taking the concentration of reactant D in molars and dividing it by 1 molar. And the same thing for reactant E. We're taking the concentration of reactant E in molars and dividing it by 1 molar. And then we're doing that in the brackets of each reactant as well. And effectively what that does is that pretty much gets rid of the units of whatever is being raised to the stoichiometric exponents. So you don't need to acknowledge that that's what's happening. You're more than welcome to just plug in the values of whatever the concentrations are for D, E, A, B, and C for your products and reactants. Just know that in reality, we're taking each of those concentrations and also dividing it by 1 molar just to get rid of all the units. Now then, just some examples of writing equilibrium expressions. If you're asked to write the equilibrium expression, or if you're asked to write the expression for the equilibrium constant of a given reaction, here's how you do it. Well, we need to take into account product concentration in the numerator, reactant concentrations in the denominator. Make sure that we're only looking at things that are in the gas state, aqueous state, or in other words, gas, liquid, and aqueous state. But specifically, if it's something that's a solid, we're not going to include it. If it's water that is in the liquid state, we're not going to include it either. So effectively, to write the equilibrium expression, well, here's how. Let's take the product, in this case, NH4OH, so ammonium hydroxide. And it is raised to the first power because that is the stoichiometry in our balanced chemical equation. We are going to divide it by the concentration of ammonia, which is also raised to the first power because of the stoichiometry of this particular chemical reaction. What we're not going to include in this particular case is the concentration of water, because as a liquid, water has a giant concentration. Usually these chemical reactions are occurring in water. And effectively what the equilibrium expression is looking at is the probability of all the products and reactants coming together. And if water is a liquid, essentially the probability of hitting water is 1, or 100%, so it just drops out of the equilibrium expression if water is in the liquid state. So to make this look a little bit more prettier, essentially I have ammonia in the aqueous state and its concentration divided by, or ammonium hydroxide's concentration in the aqueous state divided by ammonia's concentration in the gas state. I am not factoring in water. Now, let's say we have a reaction where water is instead in, say, the gas state. So it's as vapor. So it's not some giant, huge concentration. It's more in like small packets, small gas clouds that has a probability of connecting with ammonia gas. Essentially, what we're going to do is write the equilibrium expression for that. which would end up looking similar to our first expression, except we're also going to factor in the concentration of water. Now, water has a stoichiometric coefficient of 1, so we're not going to raise it to anything. And it is, in this case, in the gas state. So the equilibrium expression for this second reaction of gaseous ammonia reacting with water vapor to be in an equilibrium reaction with aqueous ammonium hydroxide is just the equilibrium concentration of aqueous ammonium hydroxide divided by the product of the concentrations of ammonia gas and gaseous water. Now, this was just an example of how do we write the chemical reaction or the equilibrium constants expression depending on whether water is in the liquid state or the gas state. Let's look at different examples where we actually have stoichiometry involved, such as the case of iron 3 chloride reacting with potassium hydroxide to be in an equilibrium reaction with iron 3 hydroxide and potassium chloride. Well, once again, we're going to factor in anything that is not a solid and not liquid water. So KEQ is just going to equal the concentration of each product raised to their respective coefficients divided by the concentration of each relevant reactant raised to their respective coefficients. Well, as far as the product iron hydroxide, it is a solid, so we're not going to include that. Now, the concentration of KCl, we will actually include that because it is in the aqueous state. And we are going to effectively raise that to the third power because the stoichiometry in our chemical equation is 3. Now, for our denominator, we look at the reactants. And our first reactant is iron 3 chloride, which is in the aqueous state. We will raise it to the first power, and we will multiply that in the denominator by the concentration of potassium hydroxide, which happens to be in the aqueous state as well. And we will raise the concentration of KO3 in our equilibrium constant expression to the power of 3. Now, when it comes to these equilibrium expressions, you don't actually have to include the physical states, aqueous, liquid, gas. You don't have to include those. I've just been including them because sometimes that's what you'll see in your textbook. But for these equilibrium expressions, all you really need to do is write KEQ equals the relevant concentration of products over the relevant concentration of reactants raised to the respective coefficients. Such as this case right here, we have the reaction of carbonic acid breaking down into water and carbon dioxide. All the coefficients are going to be 1, so we actually don't have any exponents to worry about. But we still have a product over a reactant. Now, as far as the products goes, we have liquid water, so we're not going to include it. And our other product happens to be gaseous carbon dioxide, so we will actually include that one. If this ended up, well, we will actually include this one right here. And that is raised to the first power. and we have carbonic acid in the aqueous state as a reactant. And that is raised to the first power as well. So that is our equilibrium expression for this thing. Now, what I was going to get at is, let's say you have this situation right here. Just hypothetically. Let's just say that hypothetically we had products let's just say hypothetically we had some temperature, pressure, volume where carbon dioxide was actually solid. Well, in this case, the numerator in our chemical equilibrium would just be 1, because we never include water if it's a liquid, and we never include anything that's a solid. So in this particular case, with these various physical states, the equilibrium expression would just be the inverse concentration of carbonic acid. So just know that there may be situations where essentially the top numerator is just a value of 1, or the bottom denominator is just a value of 1. It just depends on either side. Do you have things that are not solids, and do you have water that's not a liquid? To continue on, let's look at, say, liquid mercury reacting with gaseous molecular oxygen to form solid mercury oxide. So this will be an example where effectively our product's mercury oxide, it's in the solid state, so it will not actually factor in to our equilibrium expression. So we'll just have a 1 in the numerator. We will have mercury, which is in the liquid state, and we will raise it to the second power, and we will multiply it by the concentration of molecular oxygen raised to the first power. So for this top reaction, that would be the equilibrium expression. 1 over the concentration of liquid mercury squared times the concentration of molecular oxygen. And again, these are going to be the concentrations that are specifically at equilibrium. Now, this is just to go a little bit different from the reaction on the previous slide. Let's say we have instead carbonic acid reacting in some kind of temperature, pressure, volume situation where we're actually forming gaseous water and gaseous carbon dioxide. Well, water is not in the gas state. Therefore, what we're going to have is this situation where we are actually concerned about the concentration of water multiplied by the concentration of carbon dioxide. And we are going to divide that by carbonic acid concentration, since it is in an aqueous state. So in this particular case, since water is not in the liquid state, there is a probability that isn't 100%, where essentially what I should say is, if water is in the liquid state, basically water is constantly surrounding each product and reactants. Therefore, you don't need to be concerned about the probability of it actually coming into contact with, say, another reactant or another product. If water is in the gaseous state, then there is a probability of it needing to reach in order to come in contact with the reactants or products that it needs to come into in order for the chemical reaction to occur back and forth. So, all right, KEQ equals the concentration of gaseous water times the concentration of gaseous carbon dioxide over aqueous carbonic acid. And each of those are raised to the first power because the stoichiometry of this chemical equation is 1 to 1 to 1. Now, when in the case of you're working with conditions that are not at equilibrium, what you can solve for then is called the reaction quotient, which is just represented as capital Q. It's written the same way as the expression for KEQ. It's just that you're working with concentrations that you don't know for sure are at equilibrium. All right, everyone, I had a call with my boss, so I am going to do my best to get back to where we were. So essentially just re-looking at this slide. If you have conditions that you don't know for sure are at equilibrium, essentially what you're going to solve for is the reaction quotient. It's the same exact thing, whatever products and reactants and their respective stoichiometric exponents you needed to solve for KEQ, you're just going to do the same thing for the reaction quotient Q. And when it comes to the reaction quotient and KEQ, here's something that you can infer. If the value of the reaction quotient or the concentrations that all your species are at gives a reaction quotient that is larger than the equilibrium constants, that essentially means that there's too high a concentration of products and too low a concentration of reactants to be at equilibrium. So essentially, some products are going to reverse back into reactants in order to reestablish equilibrium. In other words, if KEQ is smaller than your reaction quotient, your reaction is going to shift in the backwards direction from products to reactants to form more reactants, basically. If KEQ equals your reaction quotient, that means that under the various concentrations you're at, that reaction would be at equilibrium at that given temperature. And if the situation happens where the reaction quotient is actually less than the value of KEQ, that essentially means that there's too high a concentration of reactants, and they're going to need to react and produce more products in order to get back to equilibrium. So essentially there's too many reactants, too high a concentration of reactants. Therefore, the reaction will move in the forward direction to establish equilibrium. Now then, to basically start solving all of these, to basically solve this, let's look at just one example of gaseous carbon dioxide reacting with liquid water to form solid glucose and gaseous carbon dioxide. And this reaction is considered in equilibrium. It's going back and forth. Well, one of the first things you're going to need to do is write the equilibrium expression. However, make sure that the reaction is balanced first, because the stoichiometry does factor in. So in this case, the reaction is not balanced yet, but it's pretty easy to balance it. 6 molecules of carbon dioxide react with 6 molecules of water to form 1 molecule of glucose and 6 molecules of molecular oxygen. And that will effectively have everything balanced. All right, groovy. Now that the chemical reaction is balanced, the next thing we can do is actually write the expression for the equilibrium constants. And if you're asked to do that, that's just simply what we were doing in the previous few slides, which is just taking the products divided by the concentrations of the relevant reactants. So as far as products goes, we have glucose, C6H12O6, but it is in the solid state, so we're not going to factor it in. We will include molecular oxygen. Its concentration will be involved in the equilibrium expression. And since it has a stoichiometric, since the stoichiometry is 6, we're going to raise its concentration to 6. Now, for the reactants, we have gaseous carbon dioxide, so we will include it, and its stoichiometry is also 6. The other reactant is liquid water. Now, liquid water we do not factor in. So we have gaseous carbon oxygen and gaseous carbon dioxide, the only two things that are actually being factored in, because we never include anything that's solid, and we never include water if it's in the liquid state. So, all right, this has effectively given us our equilibrium expression. Concentration of molecular oxygen raised to 6th power over the concentration of concentration of carbon dioxide raised to 6th power. Now then, what you might be asked to do is, now that you have the expression, well then, essentially solve for the value of EQ. Well, that's easy. If this first one is just you're asked to write the expression for the equilibrium constants. Next one is at the given concentrations, just solve for what the value is. Well, KEQ equals the concentration of molecular oxygen, which is going to be, let's see, at equilibrium it would be 0.800 molars divided by 1 molar, so 0.800. And the concentration of carbon dioxide at equilibrium is going to be 0.900. Therefore, all of these will give us KEQ equaling this. Let's see. So 0.8 raised to the 6th power divided by 0.9 raised to 6th power. So 0.49. All right, cool. 0.49 0.49. If we're keeping sig figs, then 0.49. 3. The equilibrium constant, it does not have units, thank goodness. So, effectively, KEQ equals 0.493. So if you're asked to write the expression for the equilibrium constant, that would just be this top thing right here. And if you're asked to evaluate what the equilibrium constant equals at the given concentrations at equilibrium, then just plug them in, whatever is relevant, and boom, this is the value. Now, let's say you're actually asked to solve for Q under these conditions. Well, that's pretty simple. If we're going to solve for the reaction quotient at conditions that are not at equilibrium, well, same exact thing, it's just we're going to be using values that are not at equilibrium. So, all right, once again, we only care about the concentration of molecular oxygen at our new set of conditions, so 0.450 molars. And the concentration of carbon dioxide is going to be 0.700 molars, or, well, 0.450 molars divided by 1 molar all over 0.700 molars divided by 1 molar. So unitless. Yeah, so 0.45, 0.7. So 0.45 raised to the 6th power divided by 0.7 raised to the 6th power would be 0.0706. 0.0706. So 0.0706. Yes. And that would be the value for Q, our reaction quotient. Now then, you might get asked, well, under those reaction quotient conditions, what direction would the reaction go to establish equilibrium? So in order to solve this one, just take into account, just compare the value of KEQ and the value of Q. Well, KEQ came out to be 0.493. So KEQ equals, KEQ equals 0.493, and comparing that to the value of Q, what we see is that the concentration, equilibrium constant, is much larger than our reaction quotients. In other words, KEQ is greater than our reaction quotient under the given conditions. Therefore, this means that as far as the direction the reaction will shift under the conditions of our reaction quotient, the reaction will shift in the forward direction. So after you're asked to evaluate Q, the reaction quotient, you will be asked, what does this mean on whether the reaction will shift in the forward direction or the backwards direction, or the forward direction or the reverse direction? Essentially, since our reaction quotient is less than the value of our equilibrium constants, that means that the reaction will go toward producing more products, or it will shift in the forward direction. That's all you would have to say. Which direction does it shift? Now, you will also be asked, hypothetically, what if you redo this problem set, all the parts that we just did, but instead of having water in the liquid state, what if you're under some pressure, temperature, volume condition where water is reacting in the gas state? Well, first things first, we just need to make sure that everything is balanced. Now then, to rewrite the equilibrium expression under this new, factoring in the fact that water is in the gas state, well, pretty simple. We still don't care about glucose, C6H12O6, because it's in the solid state. We do care about oxygen, because it's in the gas state, and we will raise it to 6th power. Now then, we do in fact care about carbon dioxide in the denominator, because it is also in the gas state, and we will raise it to the 6th power. We will also factor in water's concentration, since it is not in the liquid state, and its stoichiometry is 6. So, if you're asked to write the new equilibrium expression, taking into account that water is in a state that's not liquid or solid, it's in the gas state now, basically just put in water appropriately. If it's in the products, then it goes on the numerator. In this case, water is in the reactant side, so it gets factored into the denominator. And now then, if you're asked to evaluate, to not just write the expression of what KEQ is, but now to evaluate it, well then, under these new conditions, well, under the condition that water is now in the gas state, taking in the concentration of oxygen at equilibrium, that would be 0.800. The concentration of carbon dioxide is at 0.900, and the concentration of water is at 0.800. 0.800. And that would just equal 0.8 raised to 6 divided by 0.8 raised to 6. That leaves us with just 1 divided by 0.9 raised to the 6th, or 0.9 raised to the negative 6th. So 1.88. This would end up equaling 1.88 as our new value of the new equilibrium expression. So if you're asked to write the expression, this is all you have to do. If you're asked to evaluate it, get to the final answer by plugging in the appropriate concentrations and raising them to their appropriate exponents. Now then, redoing all this again, let's now solve for Q under these new conditions. So instead of using the equilibrium concentrations, let's now evaluate for Q at our new conditions. So let's see, oxygen would be 0.450 molars divided by molars, and carbon dioxide would be 0.700 molars per molar, so molars cancels out, and then water, which we are now factoring in, would be 1.500 molars. And that will give us a value of this. So let's see, 0.45, 0.7, 1.5. So 0.45 raised to 6th divided by 0.7 raised to 6th multiplied by 1.5 raised to 6th. That would give a value of 0.00619, 0.00620, 0.00620. So 0.00620. All right then. And to continue with this repeat, effectively, what we know now is that we know that KEQ equaled 1.88. Now, comparing KEQ, the equilibrium constant, to our reaction quotient, what we have is KEQ is again much greater than the value that we got for Q. So essentially, since KEQ is greater than the value of Q, once again, we are going to say that the reaction shifts in the forward direction. If we had the situation where KEQ was less than our reaction quotient, we would say the reaction shifts in the reverse direction, or the reaction shifts in the backwards direction. And let's see. Yeah. That would just be redoing all three parts, which is write the equilibrium expression again, but with water as a gas, and then reevaluating KEQ, and then solving for Q and determining where the direction of the reaction will shift. Yeah, that concludes our lesson on chemical equilibria. This will be very useful for moving on later on in the course. Anyways, getting incidentally up to the 42nd minute mark, it is a pleasure to have each and every one of you for class, and hopefully we will meet in person again, weather permitting. Oops. Bye-bye.